Hi, welcome to Practice Balancing Equations. Today we're going to take a look at three different reactions. Then after each one I will explain and walk you through how to balance the chemical equation. First off, you can see we put some concentrated hydrogen peroxide in a beaker, then adding some water just to dilute it down a little bit. Then to get that reaction going, we're going to add a catalyst called manganese dioxide. It doesn't actually participate in the reaction, it just speeds up the process for hydrogen peroxide to decompose to form water and oxygen gas. In that close-up, you can really see that reaction going strong. Here I have the word equation and the skeleton equation for the reaction you just saw in the video clip. Hydrogen peroxide decomposes to produce water and oxygen gas, or H2O2 yields H2O plus O2. Now we can use models to represent these molecules, and if we do that we can use little colored discs to represent the hydrogen molecules as well as the oxygen molecules, or atoms rather, and if we do that we can build a hydrogen peroxide molecule by putting two hydrogens and two oxygens together like so. That would be our original reactant. Now on the product side we need to build a water molecule which has one oxygen atom and two hydrogen atoms in it, and so that would look a lot like this right here. So if we get that built, then we can build our other product, which is oxygen, which, if you recall, oxygen is one of those 7 diatomic elements, and so it's going to have two oxygen atoms bonded together because it will always occur that way. Now notice that we have two hydrogens on the left side and two oxygens on the left side. On the right side we have two hydrogens, but on the right side we have three oxygens. And that is not balanced. We have to have the same number of each type of atom on both sides of the reaction. So therefore we have to start adding different molecules. We're stuck with these three oxygens over here because the formula for water is H2O and the formula for oxygen is O2. Therefore we would have to add another hydrogen peroxide molecule to this side, to where we have now 4 hydrogens and 4 oxygens on the left side. And in order to satisfy the balance requirement, we would want to put another water molecule over here. And now if you count up the number of reds and number of blues, or the number of hydrogens and number of oxygens, you will see that the equation is balanced. Therefore, that leads us to putting a coefficient of 2 in front of the formula for hydrogen peroxide, a coefficient of 2 in front of the formula for water. You can see we have 2 of each of those on both sides of the arrow, but our oxygen molecule is still only 1. So we will not normally write a coefficient of 1 in front, which is why I use that hollow 1 there to represent that coefficient. It is a 1, but in normal cases we would not write the coefficient next to the oxygen because it is only 1. In this reaction, you see a clear solution of lead-2 nitrate in the test tube. As the reaction proceeds, what we're doing is we're putting drops one at a time of a potassium iodide solution into the lead-2 nitrate. And as you see that solid yellow cloud forming, you'll see that that is the actual reaction between lead-2 ions and iodide ions, forming lead-2 iodide. That is not soluble in this solution. We call that a precipitate. Here's the word equation and the skeleton equation for the reaction you just saw. Lead-2 nitrate reacts with potassium iodide to produce lead-2 iodide and potassium nitrate, or PbNO3 taken twice plus Ki yields PbI2 plus KNO3. The yellow solid that you saw clouding up that liquid was lead iodide, lead-2 iodide, and that is what we're going to be showing in our models here with our colored atoms. So here's the lead atom. We're going to put with that the nitrates, the 2 nitrate ions that are associated with the lead. Here's the 1 ion, and here comes the second ion. So lead-2 nitrate is reacting with potassium iodide. So potassium has a potassium atom with an iodine atom. we go. And there we go. There are our two reactants. And now the products would be lead iodide, lead 2 iodide. And so here's a lead atom, and it's going to have 2 iodine atoms with it to make our PbI2. And then the other product is potassium nitrate, so we'll need a potassium atom with a nitrate ion. And there is our, well, almost, there's the nitrate ion. So now we have our two reactants that are forming our two products, and you can see very quickly that there's only one nitrate on the right hand side, but there are two nitrates on the left hand side. There's likewise one iodine on the left hand side, but two iodines on the right hand side. So we need to figure a way to get this to balance. If we ended up with two iodines, then we must have started with two iodines. So therefore, what we would need to do is bring out another potassium iodide molecule to react to form the two iodines with this lead on the right side. We still need to balance the nitrates as well, because there are two on the left but only one on the right. So in order to do that, we also now have two potassiums on the left. We need to end up with two potassiums on the right. So there we have another potassium nitrate ion, or another potassium nitrate molecule to come out there and make it balanced. So we now have one lead, two nitrates, two potassiums, two iodines, and two iodines. And our equation is now balanced. And you can see that we need to put in our coefficients for the one lead 2 nitrate, which again, we don't put in a coefficient normally, but I put that hollow 1 just to show that there is a coefficient of 1 for it. But there are two potassium iodides, two Ki's, so we put a coefficient of 2 in front of that. And on the right-hand side, we have just the one PbI2, and we have two KNO3s, two potassium nitrates, so we got to put that coefficient of 2 right there. Now here you see baking soda is being put into a bottle. We're going to add some vinegar. All of you are probably familiar with this reaction, so it forms a lot of bubbles. We're going to stretch the balloon over the top of that bottle to catch the carbon dioxide gas that you see being formed from the reaction of sodium bicarbonate and acetic acid, or baking soda and vinegar. So sodium bicarbonate reacts with acetic acid to produce sodium acetate plus water plus carbon dioxide. NaHCO3 plus HC2H3O2 yields NaC2H3O2 plus H2O plus CO2. Oof, that was a mouthful. But here we go with our models. Let's make a sodium bicarbonate first. We'll bring out a sodium atom. And then remember, we're going to try to keep our ions together as much as possible. So let's bring out a bicarbonate ion, an HCO3. And then to make our acetic acid, we have to have the proton, or the hydrogen atom, to start with. And then we'll bring out our acetate ion, which is the C2H3O2. And we'll put that on with the hydrogen there. So now we have acetic acid and sodium bicarbonate. And those are going to produce our sodium acetate, which means we need to have a sodium atom. Oops, like I think we'll bring the acetate ion first. And then here comes the sodium atom. So we have sodium acetate. And then we'll have water, will be another product. And the third product would be carbon dioxide gas. So here it is right there. Now what you can notice here is when we're trying to balance these things, we want to make sure we have the same number of each type of atom on both sides of the arrow. And you'll see we have a sodium on each side. We have 1, 2, 3 carbons, 1, 2, 3 carbons, 1, 2, 3, 4, 5 oxygens, 1, 2, 3, 4, 5 oxygens, and our hydrogens are also balanced on both sides of the equation. So there we have the reaction. The skeleton equation actually turned out to be balanced as it was written, because we have one of each of the molecules that were reacting and produced from this equation. Well, alright then, thanks for watching, and get out there and have some fun balancing chemical equations.